Now, as prototyping was the most important phase of our project, we had sent out rounds of prototypes to Fiona. Initially, we found out that we weren't quite getting the feedback that we needed to progress our project. Now, this is because as a shy 13-year-old girl, Fiona didn't quite possess the skills that we needed to get the feedback that we needed in the information. So, with the help of our classmates in a brainstorming session, we came up with the idea of creating a feedback questionnaire. Now, we sent these out with each round of prototypes, and it had questions on it that judged each prototype in different categories on a scale of 1 to 10. Now, what this allowed was basically for Fiona to design her own attachment, and this is the best possible way to do it, as we ultimately would never know exactly what she liked. Now, at the master's class we attended last weekend, with Adrian Antoine, he was heard saying that whatever we design, it needs to be simple, lightweight, and comfortable. And through these worksheets, we have found that we have created something that is just that. Now, the next part of our project was the SolidWorks model. The advantage of this was allowed us to start with just the basic profiles, the finger holes here and here, and design outward, instead of doing conventionally, starting with a large block of material and designing inward. The advantage of this is allowed us to design with the least amount of material and come up with the lowest possible weight, which is one of our requirements. Now, our final design is a two-piece design that clamps around the shaft of the bow, making it semi-permanent. The advantage to this is she can take it on and off her bow and try out different bows, as every bow is unique and has a different feel and tone qualities to it. The third advantage of this design is that the pommel is taken off of the bow, which does not affect the tension or the length of the bow hairs and does not affect its harmonics. Now, our final part of the project was a computer analysis. Using the next-engine 3D scanner we have in our lab here at school, we scanned in her old attachment, her new attachment that we made for her, and the violin bow itself. This allowed us to have a computer analysis in a program called SolidWorks that allows us to determine the center of mass of each bow. Now, a normal bow with no attachment, the center of mass is 11.2 inches from the end. Her old attachment had a center of mass that was 6.6 inches from the end. The attachment that we made for her is 9.4 inches from the end. This is important because the extra weight at the end of the bow effectively lightens the other end of the bow, which changes its dynamics in motion and ultimately affects the sound quality. Now, Sam's going to talk to us about the analysis of the sound.
So, the ways that we've described our new attachment differing from the old attachment have been pretty clear-cut so far in terms of weight and ergonomics. The next thing we wanted to examine was to compare Fiona's sound that she produced with the sound of her instructor, Karen Hallberg, as we mentioned, member of the Flagstaff Symphony. And based on our research, the best way to do this was to examine the two frequency spectrums by performing a Fourier transform and comparing them. So in this slide, you see in the first figure her instructor, Karen Hallberg, playing a note from DeBarrio's Violin Concerto that we recorded and transformed using the Fourier transform that I described. Essentially what this transform does is it separates the different frequencies contained within the sound produced by the instrument. So here you see the figure. You see her fundamental frequency corresponding to the highest peak appears at about 500 hertz, and then it gradually tapers off as you go to higher frequencies. Her decibel level here is minus 15 decibels. In the second figure, you see Fiona playing with her old attachment. It's the same note from the same song, DeBarrio's Violin Concerto. In this figure, you see many harmonic overtones, which are represented by the smaller peaks. And you see that her fundamental frequency appears at over 1,000 hertz, with over 500 hertz difference between the two. In the final figure, this is Fiona playing the same note with the new attachment. You see a fundamental frequency of approximately 600 hertz, which is much closer to her instructor Karen's. In addition to this, the harmonic overtones have disappeared, and the sound level has actually increased, so you see that Fiona is able to produce a louder sound with our new attachment. Moving on from the analysis, our budget for the project was $500 we were allowed. The main cost for this was prototyping materials, which came in at about $143. This would have been more except Carl's Plastics out of Minneapolis donated many of the materials that we needed. Prototyping materials that we purchased included the foam that we mentioned, woods, plastics, ball joint, and the hand forming material that we used. The final design plastic that we purchased here in town was the Delrin plastic, that black plastic that our final design is made out of. It cost $40. So you can see the total cost for the project was $183.25. So we did not use over $300 that we were allowed. We'd like to conclude by detailing some of the requirements that we had and the ways that we were able to meet these requirements. So our first requirement was that we make no changes to the boat. So with our design, it is a two-piece design that screws onto the boat. And as you can see from this image, it is removable and it does not require disassembly of the boat upon application to each boat. In addition to this, it's a universal fit. So as Fiona grows and changes, she will be able to use it on her new boats. The next requirement that we met was that it be lightweight. Her previous attachment weighed 28 grams. The boat attachment that we have made weighs only 12 grams, so it effectively changes the center of balance of the boat less than the previous one, as Matt has described. And Harvest will continue to explain requirements.
Using the plaster mold of Fiona's hand, we were able to create a complete custom fit for Fiona's attachment. The contours are perfectly shaped to her fingers and allow a cradle action so that she may get a better grasp on the attachment. We have been able to improve the texture and the problem with slipping out by applying wax to the already textured surface, which is going to help with any problems with perspiration. We were also able to increase the tone quality of her overall sound by lengthening the bow hairs, the playable length of the bow hairs, by taking the 2 inches that was taken up by the attachment before and allowing her to use them, because the thumb hole is now out and off of the bow hairs. And the last thing was that we were able to correct the tension in the bow hair at the frog by taking the thumb hole off. We would like to conclude with a few final thoughts about our presentation and our project.
So at the beginning of the school year, we had initially hoped that we could design and calculate the quote-unquote perfect solution for Fiona.
Now, we quickly realized that our design depended on Fiona's interaction and, more importantly, her opinion of the attachment. Now, the attachment that we made has met all of our requirements and surpassed all of our expectations.
As you see in this project, we are not dealing with machines, we are dealing with a human. And the most important thing we learned from, before we are thinking to design something or how it's going to look like, we should think about the customer. If he feels comfortable, she feels comfortable with it or not. Also, we had to step outside the normal scope of our education to find the right solution for our case.
Our ultimate goal in this project was to make Fiona as comfortable as possible. With a higher comfort level, she is more likely to want to aspire to a career that creates good sound out of the violin. And now, please welcome Fiona, who will play.
Small section.
She's going to play a small selection from Berrios Violin Concerto No. 9. Thank you, Fiona. acknowledgements to those who have helped us in our project. Thank you, Karen Hallberg and Jeff Robinson, for your expertise in the violin. Thank you, Mark Carroll and Fiona Carroll, for your feedback and participation in the project. And thank you, Dr. Auberly and Chris Lanterman, for being here today with our presentation. Finally, we would like to thank Carl's Plastics. We wouldn't have been able to finish this project without his help. Is there any questions?
Thank you so much. So now we open the floor for questions, please.
That's surprising. We usually get many.
Question?
Go ahead. Yes, yes.
Please.
When you asked Fiona how she felt about it,
She is prompted, and we ask her, does it feel better? She says yes.
It's kind of like there were small iterations with each prototype of just trying to address her concerns with the ways that she liked or didn't like.
And if something rubbed her hand the wrong way, or if it was comfortable, really was our ultimate goal. And you had a question?
Yeah, I was just wondering if you guys had something that you learned that you took away from this project that you really enjoyed.
Well, I learned that there's a lot more to engineering than just numbers and computers and science. There is a human side to it, especially with this project, and that it does need to be addressed.
And also we learned how success means for everyone, especially when we had the last meeting with Fiona to deliver the final project. She was really happy. We saw her smile. Her professor Karen was smiling, and her father. It's meant a lot to us because it's meant we made something.
Very fulfilling.
Any more questions?
All right. Thank
All
you.
right, there are no more questions. Let's thanks again the representatives.